Good evening, all of you. Welcome, all of you, for this live session. Let us start today's session. Welcome, all of you, for this week third live session for this Smart Grid Basic to Advanced Technology NPTEL course. I'm Gagan Meena and I'm a fourth year PhD student at Electrical Engineering Department of IIT Bombay. And we will begin today's session. Let us start today's session. We will be following the same pattern which we have been following for last two sessions. We will go through the overview of the week's content and then we will discuss some questions. You can also ask your doubts in between. Okay. So before starting the week 3, we'll discuss one one topic from week 2 also, which was not covered in week 2. And these are the deadlines for assignment 3 and 4. For assignment, the deadline is February 12th and 9. For assignment 4, the deadline is 19th Feb. So kindly submit the assignments on time. These are the deadlines for the assignment 3 and 4, February 12th and February 19th. So please submit the assignment on time. And you can find the link of these video recordings on this portal and also on this YouTube channel. Those you can watch after the session also. And this was the thing which I was talking that in the last class, while discussing the week 2, I simply mentioned that what is the impact of increase in or change in irradiance and temperature on the short circuit and short circuit current and open circuit voltage. So this is a simple mathematical proof. You can go through it. I will just explain it and you can see it again after the session. And if you have any doubt, you can again ask me. So we had discussed that this is the total photo generated current goes to this divides into these two parts. One goes to in diode current and one goes to the shunt branch. So total net current which we receive at the cell out terminal is IL minus ID minus the shunt branch current. Okay, here if first we are talking about the effect of increase in solar radiance or effect of solar irradiance on short circuit current. If you want to see the impact during short circuit, then we have to impose the conditions that during the short circuit voltage is 0 and the current will be equals to the IPV. Because This is 0. This is also 0. Under short circuit current, voltage PV, voltage across the terminal becomes 0 because we are short circuiting this. And if we short circuit this, then the IPV is equals to the short circuit current. Okay. Because if we short circuit this IPV and this short circuit current, they are same. There is only one branch. If we substitute these two values, then we will get this. Because RS is very small as compared to the shunt. This component is 0. And similarly, this component is also 0 because of small value of RS. So this becomes E is power. This becomes E is power 0. If we consider RS is very small, then the 1 minus 1 becomes 0. And these two terms become 0. They go to 0. That's why the short circuit current is almost approximately, you can say it is proportional to the IL, the photo generated current. So it's a linear, approximately a linear relationship. That's why if we increase the irradiance, the short circuit current will also increase linearly, and vice versa. If we decrease it, then it will decrease linearly. Similarly, we can also do the same thing for the open circuit condition. In open circuit condition, what will happen? This output current will become 0 and the voltage will be same as the open circuit voltage. Then if we substitute these two values, then this current is 0 and VPV will become VOC. This VPV, this is also VOC. This will also become VOC here. And then RSH is in kilo ohms and this is 20-30 volts. This quantity is very small. Okay, so this term we are neglecting. We are left with only these two terms, IL and the diode current. And then if we rearrange the terms, we will finally get this expression. Here we can see that the short open circuit voltage has a logarithmic relationship with respect to the IL, light generated current. That's why when and we know that this is having a linear relationship and this directly depends upon the irradiance. So voltage, the open circuit voltage has a logarithmic relationship. If the irradiance increases, the voltage increases very less. So similarly, we can also check this for temperature. What happens? How this voltage, open circuit voltage changes with temperature. If we calculate this, we have this expression for VOC, and if we differentiate it, we'll get this expression. And it has a negative temperature coefficient. So if the temperature increases, the VOC will reduce. The same thing we also saw in the graph. These are the mathematic relationships. You can go through them again whenever you get time. So these were the two things which from the last week two. Now we will go through the overview of week 3. In week 3, basically we discussed about the energy storage. Energy storage systems, their types, different types of energy storage, their modeling, how are they modeled in different applications. For different analysis, we require different models of energy storage. And then sizing and siting of energy storage. And lastly, the battery management system. If we see in introduction, we saw what is the purpose of energy storage, brief history, classification, then hybrid energy storage. Why do we need energy storage in power grid? and different case studies of utility scale battery development or deployment. Nowadays, the cost of energy storage is declining it's declining rapidly. Near future now. In India, also around 25 gigawatt of energy storage is in pipeline. So within 2-3 years, we will find in India also several energy storage projects will be operational within next 2 years because of the falling this declining rate of energy storage as well as because of uh, the policy because of the policy of government is funding this what we call it as the viability gap funding. The government is providing the viability gap funding for these projects. That's why the cost to the manufacturers, not manufacturer, the operator, the owner, those who will build this project, for them the cost will be reduced because the government will be bearing the cost. There are different models for energy storage development also. One is build, own and operate. You'll find in the fighting news. The same entity will build it, own it, and then even operate it. There can be other models also where a person, different entities are doing these things. Building energy storage is done by some other entity. It is owned by some other entity. An actual operation is done by managed by some other entity. This is also possible. There are some projects in Australia where the operation is taken care by different entity and the building aspect is done by other entity. That is also possible. In India, we have this model mostly. Most of the tenders are under this category. You can anyone if you tell why do we require energy storage? What is the need of energy storage? Any idea? We'll see. There are different applications of energy storage. But the main reason why energy storage came is because of it came only after the renewables. The penetration of renewables have increased. Once the penetration of renewable goes beyond a certain percentage, then managing the variability of the renewable generation in the system becomes a challenge. And if the thermal or the conventional generators are not sufficient, then it is very difficult. There are some countries which do have 100% renewable penetration, such as Ireland. Then in US there are different independent system operator. Okay, so the Californian independent system operator, they have been operating the grid for around 100 days with 100% renewable. More than 100 days out of 365 days with 100% renewable. Ireland has a majority of geothermal. Apart from this wind and solar, solar is negligible. Mostly they have wind, solar, and geothermal. They have dominance of Ireland is one country which has good, very huge amount of geothermal resources. They are utilizing it, and the role which is played by conventional resources is being played by renewable geothermal here. That's why when the ramping is required for the evening or the morning peak, if they have at least one peak is there in for any grid, that ramp requirement during that peak from off peak to peak hours is managed by geothermal resources. Here, California ISO is doing that with the help of hydro resources. So they have been able to operate the system with 100% renewable for around 3 months because of the usage of hydro for the ramping, for meeting the flexibility requirement. Wind, water, solar. They call it as wind, water, solar. And there is a book by Professor Jacobson on wind, water, solar. That yes, 100% renewable energy system are possible if we have hydro. Because we need such a resource which can provide the flexibility requirement. If we want to cut down the conventional generation because of the CO2 emission, the carbon footprint, then we need to resort to hydro. But the problem is hydro is geologic. It's dependent on the geology. Not each and every grid has that amount of hydro resource. It is location specific. That's why it is not possible for all the countries. Same way, same is the case for pumped hydro also. If we talk about storage and one of the one type of storage is pumped hydro, that is also location dependent. It depends. It requires some location. See in pumped hydro, we'll see later when we talk about pumped hydro. But yes, this was the point. Similarly, Australia also. In Australia, one state is there, Tasmania. It is also operating at 100% renewable because of solar, wind, and water. Same wind, water, solar. So they have mostly think wind. Yeah, wind is more, solar, and then water. They are also operating this because of this wind, water, solar. So if other countries they don't have, and if they want to integrate a large amount of renewable, then who will do this role of providing the flexibility requirement if the conventional is also less? If we want to reduce conventional at the same time, we want to manage the variability, then storage is required. Nuclear cannot provide such kind of energy. It's a base load plant. Nuclear cannot do that. Gas can do that, but gas also, we want to, all nations do not have even gas resources. We don't have. We need to import gas. We have very few gas peaking plants which operate only during peak hours, or for their revenue, they provide frequency regulation services. Uh, we are managing right now this by using coal, because our renewable penetration is right now it is less than 30%. But as it goes beyond in terms of energy, if it goes beyond that, then the net demand becomes very less during daytime. And the same, the duck curve which we saw in the last week also. This ramp requirement increase becomes very high, huge. And the thermal, um, some of the thermal would let's say there are 1,000 generators. Okay. And let's say because for meeting the base load, this much requirement, let's say 30% of generators are operating at their maximum because they are cheaper and cheaper generator would be scheduled first. So they are already operating at their maximum Pmax. And then remaining are 60% generators. And those who will be on bar, they must be operating at their technical minimum because that is their requirement. They cannot run below technical minimum. And we have, right, in India, thermal generators operate, their technical minimum is 55%. Okay. They are operating at, let's say they are contributing 100 gigawatt. Okay. So this much will be how much? 30% generators are running at maximum. Let's say 30% of this. Let's assume 60% is remaining. 30 gigawatt we are getting from these generators and 55% from here. 55% of remaining 60. It is like another 33 gigawatt. The total, this solar is, sorry, coal is operating at 63 gigawatt to supply this base load. The remaining, they have a capability of 37 gigawatt. Out of this, some generator, one generator, large generator would be there for spinning reserve, and some margin would be left for providing frequency regulation services. Let us assume that that is okay. Let us assume 10% is available for the reserve analysis or reserve margin is kept as a reserve margin. Okay. Now 10% is 10 megawatt, 10 gigawatt. So we are left with only now 23 gigawatt. Okay. Out of this 23 gigawatt also, there is a limit that we have, ramp limit for solar, and it is equal to 1%. Is standard is 1% per minute. In one time block, they can ramp about 15 up to 15%. 15% of, let's say, this is the remaining capacity. 15% of only of 23 gigawatt. It comes to out to be 3.45 gigawatt. In one, so what I am trying to say here is that in one time block, in 15 minutes, this 100 gigawatt of coal generation which we have, it will ramp by 3.45 gigawatt only. And in 1 hour, it will be 0.45 into 4, 13.8 gigawatt. But if the renewable penetration is very high and the ramp requirement per minute, so per time block is more than this, then coal will not be able to meet that. Then it is difficult. And out of this, if some generator goes out somehow, then it will be more difficult. And for that, yeah, we have hydro plants, so we can schedule some hydro plants. In we do schedule hydro plants during peak hours. Also, we have hydro plants, gas plants who have very high ramp rate. They are peaking plants, but they are very costly. Hydro, and then next option is we have batteries. If we can charge the excess solar during the daytime, we can release that energy stored in the battery during the peak requirement. These are the battery. is the battery capacity around the world. If we see 27.1% of the battery installed capacity, battery is one of the technologies of the pumped hydros. Sorry, one of the technology of energy storage. And in battery, we saw last week also China, China dominated in solar, in renewable energy sector, and here also in storage because we saw that in last week China has such a huge renewable penetration, very high renewable penetration. So energy storage would be required. They have pumped hydro also and battery storage. We see 27.1 gigawatt of energy storage. It can quickly ramp. Entire battery storage can ramp from zero to maximum within one time block. Uh, Let's see if they have 25 gigawatt also operational. Within one time block, they can provide the battery can provide 25 gigawatt of power, and the solar goes down. So it's very uh, essential when the renewable penetration is high. So these are the different applications of energy storage where we can use them. First, so these are categorized into these four groups. One is system operation. This we have already discussed. Frequency regulation. The system operation services are frequency regulation. We call them ancillary services, right? We had discussed them. That one of the type. These are types of ancillary services. Flex start requirement, frequency regulation. In this also we saw primary, tertiary, primary, secondary, and tertiary frequency regulation services. And then flexible ramping. So energy storage can help in this. And then investment deferral is a very classic example of investment deferral is why do you want to defer? Means how energy storage can help here. You see transmission. Building a new transmission line requires planning beforehand and its construction also takes time. We have to first of all procure the right of way, the land requirement, the if this is the transmission, it's so this is the transmission line. Then on the both side of this transmission line, this much land is required. This is called right of way. Because the PGCL needs to purchase that land, procure that land for erecting the transmission line, and then construction of transmission line also takes time. Also money. Cost is there, land requirement, and then also the time for completion. It takes time, it's very costly, and our land requirement is also huge. And because land is involved, many a time it's become very difficult to procure the land. There are protests sometimes. Because most of the lines you would see they would go through agriculture fields. Those farmers who are practicing there, they are disturbed. Sometimes it creates problem. It creates problem, and we see sometimes the right of way falls through ocean, through rivers, or over mountains, hilly area. In those area, construction takes more time. It takes longer time. If instead of this, if we have some other option, which is quick, implementation is quick, and it's modular, scalable, can be uh, can be constructed anywhere. Land requirement is land is required for energy storage also, but it is less. And yes, implementation is fast. Very important thing. So if we can use energy storage and relieve the congestion on transmission system, why do we want to build a new transmission line? Because either there is a new load at a new place and at a remote location, new load area which is to be connected to the grid, then transmission is required. Another uh, requirement can be when the existing transmission system is overloaded or congested and it cannot transfer more power. Then we need to erect a more transmission lines, either parallel to that corridor, a new parallel corridor. So energy storage can help in relieving the transmission congestion or distribution congestion also. And if we are able to do that, then we can avoid constructing the new transmission line by few years. And by the time, because it takes time. So by the time energy storage can provide that relief, congestion relief, and within that duration, the transmission line can be constructed. We can defer that investment for some time. And apart from that, also energy storage can provide other services where which we have it, these system operation services also. So even if when new transmission line is built, it is not that the energy storage role will be uh, over. Initially, it was built for relieving congestion, but it can uh, provide other services also. And also, because energy storage is right now costly, energy storage is not used for a single service, for providing only one type of service. It is used to provide stack of different services. So it can be ancillary service, capacity, it can trade in capacity market, it can in energy market, it can also provide services in energy market. It can provide the black start is covered here also. Yeah, congestion relief here. In that case, it will be a transmission asset or transmission services. The transmission operator uh, can have some contact with energy storage to provide this congestion relief services. These are different types of services which a single energy storage plant can provide. This is a portfolio of service which the energy storage can provide. It's an optimization problem which the storage owner will have to solve. How much of the capacity, let's say the capacity of energy storage is not, let's say 250, let's say 100 megawatts. Then the owner, the operator or the owner of the storage that needs to decide. First of all, it cannot deep discharge it and cannot overcharge it. Let's say the limit is 90%. So it becomes 90 megawatt on the upper side and lower, let's say it is 10 megawatt. The usable capacity is only now 80 megawatts, which is remaining with the operator. Now the operator has to divide between these different four types of services: ancillary services, congestion relief, capacity market, and energy market. Now, how to divide? How much to keep for which service? It's a very difficult question to answer. And for that, we need to solve that optimization problem. And it depends it because finally the operator wants to make profit. So what should be the optimal split of this 80 megawatt among these four services so that the operator earns a profit. Okay. In that case, energy storage can a single owner, single energy storage can provide all these kind of services. Not this grid scale energy storage would. This is for mini grid. For example, if a mini grid has a diesel generator, we all have seen in big commercial complexes, industrial complexes, there are diesel generators for power backup, providing backup power. In that, if we have energy storage, then we can use energy storage instead of diesel generator. We can reduce the reliance on the diesel generator. But these services, the grid scale energy storage can provide. System operation we have discussed. Investment deferral, yes. Capacity deferral. Congestion relief we have talked about. Then energy shifting. Yes, this we again we discuss this topic. We see that so this is the let's make it more simple. Let's say this is the daytime, and here we have excess solar generation. So this energy can be stored in the storage, and this energy then storage can release during off-peak hours. So energy, we are shifting the energy from one time to another, and this will make uh, and in effect what we are trying to achieve. We are trying to achieve a flatter load curve, a more flatter load curve, load profile. Okay. In this case, energy is also shifting, and we are also reducing the peak. So it is also peak shaving and energy shifting, both are happening in this case. Then renewable integration. If solar and wind generation is much more, let's say during the daytime, we already know that the coal generation, they have a technical minimum. There is one very peculiar thing which we'll find when renewable penetration is quite high. It is observed that the demand, the net demand, I would say, net demand, which is equals to demand minus the renewables, contribution from renewable. This net demand, the net demand is less than the technical minimum of the generators, co- coal generators. Let's say this was the technical minimum of the coal generators, but the demand profile becomes like this during daytime when the solar penetration is quite high during peak solar hours. So this becomes a problem. Now conventional generator cannot reduce. They have to operate on technical at technical minimum, and demand is even less than that. Now what will be the problem? Demand is more than generation. What will happen? Can you tell what will happen? So earlier we are always concerned about peak demand, that the demand is more than generation. But here the problem is generation is more than demand. Because of renewable, we are facing this challenge also. In this case, we cannot reduce coal generation, and we cannot even increase the demand. How can we do that? If we don't do that, then frequency will increase. And if frequency and we want to keep it between a tight band, the here storage can help. Otherwise, if storage is not there, what we need to do? We need to reduce the generation. We cannot reduce the coal generation, then we need to reduce the generation from solar or wind. Then curtailment will be there. The renewable output has to be curtailed. Although generation is there, but it is not going, it is not allowed to be fed into the grid. So that there is a wastage of solar generation. If storage is there, then what storage will do? It will act as a load. It will charge. It will increase the demand. It will bring this curve above. So excess solar generation can be stored by storage and it can be released during the evening peaks when ramp requirement is there by the coal generators. That time energy storage can help. Okay, renewable integration is done. Yeah, the application you have seen. These are different types of energy storage. We have electrochemical. All the battery energy storage fall into this category. All battery energy storage systems. Lithium ion, sodium sulfur, means lithium ion, sodium sulfur. These are I'm talking about grid scale batteries. Then we have metal air. One is sodium ion battery also, just as we have lithium ion, sodium ion battery. Metal air, zinc air batteries are there, iron air batteries. They can also provide grid scale services. And then there are redox flow batteries also. Redox flow vanadium, so VRFB, the vanadium redox flow battery is example of the redox flow batteries. Because these all they are part of electrochemical energy storage. In electrical, we have two. One is superconducting magnetic energy storage, and one is supercapacitor based. What is the principle used here in supercapacitor? We have heard about capacitor. You know, capacitance is silent. But this is the formula for capacitance, right? Since if you would have seen capacitor that we generally use, you will find the rating in millifarad, microfarad, nanofarad. In farad, uh, we don't see capacitance in farad. But these supercapacitors, they are rated in farads. So what do they do? If you want to increase the capacitance, then how can I do that? Either increase the area or reduce d, the gap between the two plates. We cannot reduce the gap beyond a certain limit, right? So what is done here is area is increased. How? The surface area of the plates are increased. The material used here is such that it's porous. Very highly porous material is used, and because of that the overall surface area is increased, and because area is increased, capacitance increases. That is the basic principle for this superconductor energy storage, supercapacitor energy storage. And this is a high power density device. These two are high power density device. They cannot provide very long discharge durations. That's why they are used where we required very flash. Let's say for flash charging, you have heard. There we can use these supercapacitors for providing this. primary frequency regulation services, we can use there. Is superconductor, supercapacitor energy. Similarly, is SMES also. Then the next category is mechanical, and in mechanical, we have different types of energy storage. The most widely used energy storage in mechanical category is pumped hydro. And if we see presently the overall capacity, installed capacity in terms of installed capacity, pumped hydro is the dominant technology used. It's an old technology, pumped hydro. In India also we have many pumped hydro energy storage, and now many new are under construction. Terry is a very 101 gigawatt pumped hydro energy storage, Terry power plant. Terry. And in Maharashtra we have Ghatgir, I had told you. In there is one project in Andhra Pradesh, Pinnapuram. It's also a pumped hydro energy storage. There are many such projects. So that is one pumped hydro. Here we have two reservoirs. One is lower and one is upper reservoir. Now these, I was talking about pumped hydro that it is location specific, but there are two types of pumped hydro. One, one are very big, large scale pumped hydro, which are generally at least one of the reservoir would be natural reservoir. Mostly it is the upper reservoir, but it can be lower reservoir also. Generally, one of the reservoir is natural reservoir, but if both the reservoirs are man-made and on a smaller scale, then they can be built in city area also. If some a small scale pumped hydro storage. In that case, we need to fill those reservoir with water because those are both are man-made, and they will be small scale, smaller pumped hydro plants. And there is one paper they have conducted this study around the world in each and every country. What's the potential of such kind of pumped hydro storage, which where both the reservoirs are man-made? So they have found out for India also, but we don't have right now those. And most we have large hydro pumped hydro plants where at least one is a natural reservoir. In Maharashtra also you will find the upper reservoir is the natural reservoir. Lower is a man-made reservoir. So the operation of the pumped hydro is limited by the capacity of the lower reservoir. And its operation is also very dynamic in monsoon. If you see this upper reservoir is already filled, and then we cannot pump water from lower reservoir to upper reservoir. In that case, we can only generate. Already it is full and monsoon is there, we can simply generate, keep on generating and generate here and fill it here. But now because you cannot pump it, so you cannot generate also because the lower reservoir is already filled. So in monsoon, its capacity is reduced because if both are man-made, then that problem is not there. It's a flowing reservoir. It's a natural reservoir. Water is coming inside, and if it is full, then we cannot work with the lower reservoir also. Pumping is restricted here. Okay. So this is pumped hydro, and in mechanical there are other reservoirs also. One is flywheel, which uses the kinetic energy stored in the rotating mass. Then gravity based. There are many companies now which have come up with these gravity based energy storage. Here, land requirement is also very less. You can have a gravity energy storage in one building also. It is kind of uses a kind of crane and a lift mechanism where there are these huge blocks, heavy blocks, which are pulled up. Then by using the lift, they will be pulled up and kept here. Now they have a potential energy. We have increased their potential energy. So this is the charging process. Charging process. The energy is stored in the form of potential energy. When discharging is required, then they will drop it, release it, and that energy will be converted into kinetic energy and can be used. That is gravity-based energy storage, and then one more is there. This compressed air. In this, we require. This also requires uh, reservoir kind of thing, but it's not open. It is closed. In underground salt caverns or these underground mines which are no longer used for mining purpose. Such sites are utilized here, and the air is compressed here. The charging process is to compress the air in these underground caves, underground tubes, wells, and then when discharging is required, they will release the gas. And here we have the turbines generator system mechanism to generate the electricity. Okay, the mechanical is done, then thermal energy storage. Yeah, these are also of different types. In one we saw last time also solar thermal energy storage. There is one sand battery also. There is one company which have come up with sand battery. They heat the sand to a very high temperature, more than 1,000 degrees, and it is the structure is made such that the loss of heat is negligible. It's very less. It is there, but it is very less. Just as we have these thermoflask bottles, for 24 hours we are able to maintain the temperature. Not for 20, then at least yet for 20 hours, 10 to 15 hours, we can maintain that temperature. So they use that technology and maintain the temperature of the salt. And whenever the requirement is there, then they will use that heat from that salt to steam the water, and they have used that technology, that sand battery in Finland. So these are these European countries, Scandinavian countries. Their temperature is quite low in winters, and the district cooling requirement, heating requirements are there. For that, directly they can use the heat to boil the water and then supply that heat, that boiling the hot water for the heating purpose. So this thermal energy storage has more utility in for decarbonization of industrial processes. And some technologies like molten salt energy storage, they can be used for grid scale and as grid scale energy storage also. But others can be used to indirectly reduce the demand by decarbonizing the industrial processes. If we are able to meet the heating requirement by this thermal energy storage, then the requirement for electrical heating would reduce. The demand would reduce. So it's a very good method for that. Then chemical are also there. Hydrogen, which we are talking about nowadays, it falls in this category. And hydrogen can provide a long discharge duration. Its energy density is high. Yeah, these are the hybrid energy storage system, let's say we have a battery and we want to provide the primary response services, primary frequency regulation services. For that, we know that this service is provided for a very short duration and it is a very frequent service. So short duration plus frequent. You can say intermittency is quite high here. And we know that this charging discharging cycles, if there is a limited number of charging discharging cycle for any battery, and if we have a frequent charging discharging, then it degrades the battery, its life reduces. What can be done is we can have a flywheel or a supercapacitor here with the battery. So these short duration fast response services can be provided by this flywheel. And the longer duration, the secondary or tertiary frequency response services can be met by battery energy storage. These are the different combinations. So here we are taking advantage of the energy density. Let's say in comparison to these, the energy density of battery energy storage is high, and they have very high power density. They have high energy density. So these two complementary properties, if we combine, so these two technology have these two different property. If we combine them, we will get a good output. We can get both high power density. We can meet both type of demands. That's why whenever hybrid combination, we saw in the last week also. Why do we want to combine solar and wind? Because of their complementary nature. In daytime, solar is there. Wind is more during night time. Right? Also, we saw during some season, during monsoon season, wind is quite high, but solar is less. It's complementary. Both they are overall they are able to improve the capacity utilization factor. Same thing here. We want to do. We want to reduce the degradation of the energy storage, and we want to provide both fast response as well as long discharge duration. These both type of application we want to meet by using a same one entity, one storage device or product, we would say, because here we are using two technology at a time. And this is also used in these electric vehicles. In electric vehicles for initial acceleration, it is a fast response service, acceleration. But if we use lithium ion for providing that, its its degradation will be fast. It's not that we cannot use, we are using it, but it will reduce the cycle, the life of the battery. And there, if we use the combination of the two, supercapacitor plus lithium-ion battery, we will see one example also. So these are the possible combinations: supercapacitor plus hydrogen. So these are technology which have high power density, and these are relatively higher energy density with respect to this. The supercapacitor hydrogen combination, SMES lead acid flywheel. Then we saw battery and compressed air, battery and fuel cell, and battery and supercapacitor. I think I have this should come here, and supercapacitor should come here. Supercapacitor is a high power density device, so I should change this. It should come here and it should go here. Okay, so these are some real-time examples. In US 2016, the combination used a supercapacitor and battery for load shifting and RES smoothing. Then lithium ion and Chile, lithium ion and hydrogen. Lithium ion and sodium sulfur. Sodium sulfur can provide a uh, longer discharge duration. Then vanadium redox flow also here. Why redox flow battery and lithium ion? Because this here the frequent charging discharging doesn't affect the degradation. It doesn't degrade the battery. And also it provides a deep discharge. We can have deep discharge here. It is possible for vanadium redox flow, but it's not possible for lithium ion because they it has two tanks for these electrolyte, separate tanks. So independently we can increase the power density here. Oh, sorry, energy density independently of the power density, but it's not possible in the lithium ion battery. We see these are the real-time case studies for battery energy storage. We were discussing that a battery will provide the RAM to help to meet the ramp requirement. Here we can see this is for KCO, California Independent System Operator. See in the daytime this much is a solar. You see very high solar and this is used to charge the batteries and then batteries are discharging. You see this much requirement batteries are providing around 7 to 8 gigawatt of power from battery. It's coming from battery. That's quite high, quite large. Here also you see in morning also they are providing ramp requirement. They are meeting the ramp requirement and here also in the evening for the evening peak. Similarly, you can see this is for ERCOT for Texas. Here also you see battery. The battery peak at 4.5 gigawatt of energy storage. Supply from energy storage for providing the evening peak. In US and Australia and now China also, they have very good, very large projects, especially the world's largest project you'll find in Australia and US. And we saw in the first week also that Dubai is coming up with this 19 gigawatt hour, 1 gigawatt base load plant. It's also a huge plant, very huge plant. The next we discuss different battery modeling methods. The first one is electrochemical method. It's a very detailed method. Here we will have to write that electrochemical, the Gibbs energy and all those things we need to model here. And then another approach is equivalent circuit model. For different application, it depends on what process we want to study. The details required, the model used, it depends upon the application. If we want to track the details at millisecond level, microsecond level, then the model has to be very detailed. It has to be capture each and everything. And electrochemical models are required in that case. But if you want to have only a steady state operation of energy storage, then simple equivalent circuit model is also sufficient. And even empirical model will work in that case. Simple equations of energy storage, how charging discharging equation, how these are related, charging and discharging operations are related, even that is sufficient. We don't want to model the transient. So depending upon the requirement, these different models can be used. In optimization, we use simple equations, but those can also be made detailed. Now there are some papers which uh, they are making these models for lithium ion more detailed, where The most commonly used method is model is for optimization is that the discharging power will be within 0 to its maximum limit. Similarly, charging power also between 0 to maximum limit. And then charging and discharging cannot happen simultaneously. Their product has to be 0. And then one equation is for the state of charge or energy update equation. So it will depend upon the energy in the last time block plus some charging which is happening. If charging is happening, it is multiplied by efficiency P charging. Then discharging into delta T. Delta T. And this energy also is within a maximum limit and a minimum limit also to prevent deep discharge and overcharge. This is the most simple method. But if we want to account for the change in efficiency, efficiency is not constant throughout. As the SOC changes, efficiency also changes. Efficiency depends upon the voltage also. So if SOC is changing, efficiency is also changing. And if we want to incorporate that, then we need more equations for that. Then even this charging discharging rates, it also changes. We cannot here it says that anytime we can have, irrespective of these SOC, you can charge and discharge at any rate. But that is also not true. As the SOC increases, the discharging or the charging rate reduces. You cannot charge at a very high rate. The charging rate also changes. It is also a function of SOC. So model can be made very detailed also, but it depends what we are trying to study. To what details we want to model. Okay. So this is the equivalent circuit model. Here we have a voltage source and then a parallel resistance. So this is the voltage source, ideal voltage source you can say. But then in series, this is ideal voltage source, and then in parallel we have a resistance, practical voltage source, and then in series also we have a series resistance and one RC, number of RC branches. It's a two-time constant representation because we have only two energy storing elements here. C, two passive energy storage element, two capacitors. If there is only one, then it will be a one-time constant representation, only one. If this is not there, then it will be one-time constant representation. And it is also called a ladder circuit. If we have one more, then it will be three-time constant. The more we increase these numbers, the model becomes more accurate. But then the time required to solve that model also increases. So there has to be some trade-off between the two. And finally, we discuss the battery management system. It's a very important part of energy and for any energy storage system. You would have heard of these heating problem, the battery catching fire. Right? These electric vehicles, two-wheelers, four-wheelers, they're catching fire. It can be because of many reasons. One reason is the thermal management is not good, and that can be because of a poor designed battery management system. Because battery management system, it also tracks the temperature of each cell. And for cooling requirement, we have other. And after once it detects that the temperature is high, then there are methods to cool. But the step to reduce the temperature to ensure that the temperature is doesn't go to such a high level. That is ensured by battery energy storage, this battery management system. So it helps us to detect any kind of hotspot which is there and to prevent that. It has many functions. Battery management system, it also, suppose in if we have a car and we are going from one city to another city, let's say it's a 300-kilometer distance, and we are going by an EV, electric vehicle, then we are always worried about the, if petrol is there, we can see the indicator, right? Indicator is there, you see that the petrol, the indicator is showing red. That means we need to refill it. Because petrol, for measuring petrol, in, an indicator for petrol is very easy to, you can easily monitor that. This is the level of petrol in the oil tank. It's very easy. But for energy storage, for battery, it's little difficult. And let's say if the estimation of the charge energy level which is available in the storage is not correct, then what will happen? We will think that, let's say the indicator is showing 50% energy level is still there in the battery. So they are hoping that they will at least they will be able to cover around 150 kilometers. And so they thought that okay, we will let us cover around 60, 70 kilometers, then we will charge. But they some if the algorithm is not correct for SOC estimation and the, let's say the indication was 50%, but the actual was only 30%. And we know that we cannot go below 20%. Here we had a difference of 30%. Now here there is a difference only of 10%. And there is a wrong indication of SOC. In that case, it will be very difficult for the driver of the electric vehicle. That's why this measurement is very important. Similarly, the state of health is also very important. It tells how much cycle, how many charging discharging cycles are remaining. It measures the health of the battery. All these things are very important. So it measures current voltage and temperature of each cell and does cell balancing, which is also very important. If two cells are there in series and one is not able to charge because because of capacity fading, it has reduced, its life is gone because of deep discharging. Somehow this one cell went into deep discharge and just it has degraded, its capacity is degraded, and this is fully charged. And if these two are connected in series, then what will happen? If we want to charge it, this will not allow because they have to carry the same current, right? And if you want to discharge it, then this will not allow. Yes, you want to ask something?
Yeah, SOH, can you explain a little bit? Is it related to charging discharging cycle, or is it similar to SOC? I mean, the reciprocal of it.
No, no. SOH is not reciprocal of SOC. SOC is telling us how much, let's say, we have this 0 to 100% capacity of battery. So SOC is simply telling us if it is fully charged up to 100%, then it will tell us that SOC is 1. If we are, if SOC is from 0 to, of let's say percentage only, then SOC will be 100%. So it is state of charge. That means how much charge is there. What is the status of charge? in the
You mean to say
battery.
the end cell voltage kind of thing? Like up to what lower voltage the cell can go? In that sense, say the conventional cell is 3.65 volt
Hmm.
per cell I'm talking about, and
Yes.
say I have more experience on nickel, cadmium, and lead acid. That's why I'm asking this.
Okay.
Lithium ion, I have little experience. So in nickel, cadmium, or lead acid, there's an end cell voltage
Hmm.
beyond which you discharge. Then you may uh, deep discharge the cell, and the cell
Yes.
may
Yes.
not come back. So
Hmm. Actually, the SOC, you are correct. SOC and voltage are related. Let's say this is 0% of SOC and this is 100%. Then this 0% is achieved at a certain voltage. So this is 3.5 voltage and this is 4.2 volts. And we want to prevent it from deep discharge, then for 20% the voltage level will be something. Let's say 3.7. And the voltage is in between this range only, from 20% to 100%. Based upon SOC, the voltage will change. It will change. And we want to keep it within the safe range. We don't want to deep discharge it, and also we don't want to overcharge it. Therefore, once the voltage is reached, then that's why the charging operation of this lithium ion battery, it has two regions. One is constant current region and one is constant voltage region. So we call CCCV curve. So this is a constant current region where the voltage will build up. And once the voltage reaches that this final, the rated voltage, then the voltage will be held constant and the current will be increased. Okay.
yeah. That is the same case with any conventional charger,
Yeah, for
lead
any,
acid.
yes.
But now, okay, now we were on SOH. So what is how to? Can you explain? I cannot understand that.
So
SOH.
SOH is for the health of the battery. Let's say the life of the battery was, let's say, for 8 years. For cars, the companies are providing warranty of 8 years. Let's say the the life was 8 years. The initial life was 8 years. In that case, if we see the status of battery, when we purchase it, it will show 100% state of health. It will be able to mm, uh, provide satisfactory performance up to 8 years. But now, depending upon the behavior, what how we have charged, used the battery, how we have charged, how frequently we have charged. For each battery, we will, since there is one slide, yeah, this one. So for each battery, there is a degradation curve. So this number of cycle versus depth of discharge. And this relation is also there with respect to discharge rate also. So this degradation depends upon number of factors. The two most prominent factors are depth of discharge and discharge rate. The rate at which it is discharging, and it also depends upon temperature. But these are the two most important uh, factors. Now, if we are discharging the battery, let's say we are discharging it to up to 10%. Say if we are discharging it only up to 90%. So as soon as it reaches 90%, we are charging the battery. Then its life is this much. But if we on a regular basis keep on discharging it up to 10% or 90%, the state of charge is equals to 1 minus depth of discharge. If depth of discharge is 90%, that means the charge left is only 10%, and we keep on discharging it up to 10%, then the life cycle reduces to only 1,000 years. So sorry, 1,000 cycles, only 1,000. So reduction of it becomes 1/5. On the top of it, if discharge rate is also applied here, we are discharging it at a higher rate. You see, since we can see the curve here also, these are for different discharge rate only. This is for this 0.25C means in if we discharge the battery at rated power, it will take 4 hours to discharge completely. That means 0.25C. 5C means 60 by 5. It will discharge completely in 12 minutes. 5C. If 6C is there, then in 10 minutes it will completely discharge. Now, if we change the discharge rate, then for 5C, you will see for the same depth of discharge. For 0.25C, the number of cycles is around 30 to 50. And for 5C, it is around 2700 only. So the way we use the battery determines its life. And that is because of the degradation. And the degradation is captured by in one sense, it is estimated by a numerical value is given to that by this state of health. It will show us a number from a scale of 0 to 1 or in percentage and 0 to 100, just as we have SOC. Is it is it fine?
Yeah, thank you. I got idea.
Yeah.
A few more questions coming out. If it's not delaying, can I ask?
Yeah.
Now, as you said, for the 5P, 5C or 0.25C,
Yes.
practically 5C or more than 1C batteries are available in the market, if you're aware.
LTU, you will see. I have shown, I think, here.
In the lithium
Yes,
ion category.
these are the different chemistry for lithium ion batteries. The most popular which we use in electric vehicles right now is this
Lithium iron
LFP.
phosphate.
Yes,
Right, right. So is
and
1C, 2C available? Because 1C probably maybe, but 2C
yes,
or 3C or
LTO. I commercially these are yes. There is one company in I don't remember either Japan or some country. That is the only country which manufactures this LTO chemistry. They have monopoly over that. And the fast chargers which we are talking about, that the fast charger right now, those fast charger which we have on these highways, they there also it will take around 40 minutes to charge the vehicle. In that case, the chemistry, the battery has to be more than 1C. Because if you see the Tata, this Nexon, if we charge it at home using our simple 15, this 6 ampere socket, then it will take around 15 hours. But if we have a onboard wall mounted charger, some Mahindra provides one wall mounted charger of around 7.5 kilowatt or something. So then the charging time reduces by half. Within 7 hours, 7 to 8 hours, you can charge it. But using fast chargers, you can charge it on the fast charger which are available on highways. You can charge it within 40 to 60 minutes. So that battery is operating at different discharge charging rates in these different scenarios. So one chemistry can support. So if we, yeah, see here we are seeing LTO can support all these different charges. So if we are using LTO up to 2C, it can provide. NMC also can provide that. So these batteries are available, but 10C I don't think it is available right now. LTO is there, but 10C is right now not available. Even up to 6C, we are talking about 6C, that in future the will be able to charge the vehicles within 10 minutes, just as we fill our diesel or petrol tanks in the vehicles. In these uh, two wheelers, the most batteries are around 0.3C or 0.2, 0.3C. Because the more we increase this charging discharging rate, cost also increases. An electric vehicle, two wheelers, cost is a problem. We cannot have. That's why this thermal management system also, if good thermal management system are costly. Now they are changing things and trying to make develop a good thermal energy store, thermal store, thermal
Management
system
system.
management system. Yes, correct. For which is cheaper.
Mhm.
So yeah,
Okay.
these chemistries are available. Some are under in research. 10C is under, we can say, research. But yes, LTO is there commercially available. But I don't know exactly up to how much. Exactly what is the largest C rating available right now in the market? That I am not aware of. But these all these chemistries are, yes, commercially they are available.
Okay. Normally, what we see in the market for a large scale application for a grid scale
Yes.
energy storage is 0.5C.
Hmm.
1C would be a special application. It would be
Hmm.
easily available, would be a zero point 0.5 or 0.25C.
Yes, yes,
So
correct.
1C is not so easily available. Again, the limitation is the thermal management system. It need
Yes,
to have a
yes.
higher, a better cooling system for the batteries.
Correct. Correct.
Okay, thank you. Thank you.
Okay. Okay, yeah. So these are the different uh, roles of battery management system. It will measure these different quantities. It will ensure cell balancing, which is also very important for some aspect of utilization, proper utilization or full utilization of energy storage, as well as from the point of view of thermal management. From both the point of view, cell balancing is very important. And then it also estimates the SOC and SOH, which is also very important to know the status. And then it will compute these different limits. Thermal management is also part of it. Cooling requirement is cool design of that cooling system is different, but the sensing of temperature, keeping it below the limit, all these are part of battery management system. And then protection against different types of faults, and finally communication. And these are different advances in the battery management system. Now, wireless communication between different battery pack modules. Initially, now also in big these grid scale energy storage systems, these modules are connected. These are wired. But now on smaller scale, you can have this wireless BMS, then smart BMS, and then finally this digital twin, AI powered digital twin cloud BMS. Have you heard of digital twin? This is
Yeah, yeah, yes.
nowadays it is common. It's not a new term, I would say. We have been using this for a long time. So we can say this SCADA system is a kind of digital twin, but not to uh, that extent which we are talking about nowadays. One example of digital twin is to these autonomous cars. or you can take simple example of wind turbine. We have wind turbine, physical wind turbine is there in some wind farm. And in control center, we have a detailed model, physical, mechanical model of that wind turbine in a system. Okay, so that model exactly models that physical model to a very high accuracy. That model is a digital twin, and these two models, one is the physical model, which is there in the wind farm, and one is the mathematical model. It is there in the control center. And these two models can communicate with each other because this physical model will have many sensors, and those sensors will feed the data via some communication channel to the control center. And we have already seen this SCADA, RTU, all those things. Then the control center can send some commands to the physical model. In that way, simply from the control center, we can control, we can monitor many things. We can optimize its operation also. It is possible. So here, similarly in BMS, one physical BMS is there, and one BMS mathematical model is also available. A physical model of battery is that mathematical model of battery is available on the cloud, and the computation, whatever SOC estimation, everything is happening on the cloud, and it is again it is being fed back to the actual physical model. Similarly, one can have a digital twin of autonomous cars. Autonomous car is a physical device, and it can have its entire detailed mathematical model on the cloud, and it can communicate. The two models can communicate with each other. And these cell imbalance can happen because of these different reasons. And we already discussed that a cell with lesser capacity, it will tend to discharge faster than the other, and then it will premature earlier than it will premature. Then it will create problem. We don't want that. For that, different types of cell balancing techniques are there. Passive is simply to have a resistor, and this passive technology works on equalizing voltage. And these active balancing system here will be having capacitors, and these more advanced we can have switched capacitors. Here it is fixed capacitor, and here then we can have switch capacitor, and we can also have power electronics interfaces for that, for more better control. Here the aim is to equalize voltage. Here the aim is to equalize the energy levels, trying to maintain the SOC, same SOC level. Here, different approach. We, so why batteries we have already discussed, but out of energy storage, why batteries? That also we have
Which
already
is
discussed.
more,
Sorry,
more energy efficient?
oh sorry,
Uh,
I
which is
could.
more energy efficient? Well,
And
energy efficiency.
this one is more efficient here. Unnecessary drop across resistance is there. That is why we move to active. It's same as we see earlier. We were having those regulators for fan, right? Those were resistive. Big box you would have seen. There were heating losses also across the resistor. But then we moved to power electronic based triacs for regulating the voltage regulator, power electronic based regulators. They are very efficient, high switching devices. It switches at very high frequency, and the heating loss is also reduced. Active balancing is, that's why here we see it exchanges the energy between high capacity to lower capacity cells without dissipation. But here the voltage equalization happens with dissipation. Because the charge is it is it's bleeded into the resistor. We are simply losing that energy. Right? If this is at a higher voltage, say zero point 0.4, and this is at 4.5, this is at 4.4, then there will be a current here, and there will be a heating loss here. Then so this, and because we are equalizing voltage here, the SOC will be the energy which was some part of that will go into the resistor and it will be lost. But here we are avoiding that. Dissipation is not there, or it's very less, because ideally some resistance is always there. Practically it is always there. Ideally there is zero resistance, but here dissipation will be very less, very less. So we have already discussed why batteries. And then yes, I was talking about one example of hybrid energy storage, right? Here, this is one example, Gemini battery for energy for electric vehicles. And they recently, in it's 1 or 2 days ago also, this was in news. This company, they have come up this Gemini 2, which is also a very good battery. Here, they are using two technologies. And the advantage is that it uses 20% less lithium and 60% less graphite, and also providing a very large range, driving range of 965 kilometers. The first 20 to 40 kilometers, it uses LFP battery, and then it shifts to the lithium manganese oxide for the remaining battery. So it is a hybrid of two technologies. And that's how they are able to provide a wider range, driving range. What is happening? I'm not able to. How it is hanged. Wait just a minute. I'm not able to change slides. Yeah, sorry for the inconvenience. There was some problem. I'm sharing slides again. I hope it's visible now. Is it visible?
Yes, sir.
Now it's in the full screen mode. Okay. Now we'll move to the questions. The first question is, which of the following is not an electrochemical energy storage? Very simple question. We have discussed all the different types of energy storage systems. So what's the answer? Correct answer? You can type in the chat box also. So which one is the correct option? Which one is not an electrochemical energy storage system? Chemical has come twice here. Anyone? As we saw, so synthetic fuel, correct D. Synthetic fuel, hydrogen, we saw. Ammonia is also one example. All these are chemical energy storage. Above are rest three are electrochemical. Correct. Two battery aging phenomena. What are the two aging phenomena? D. Correct. Calendar and cyclic. So these are the two phenomena. Calendars aging is because of inherent degradation. We cannot prevent it. It is there gradually. It and because of this aging only we define the life cycle of the battery, number of its lifetime of the battery, and this can be further reduced by this cyclic aging. And it is due to the discharging and charging cycles. So it depends upon depth of discharge, discharge rate, limits on SOC, and ambient temperature. We have already seen this curve. So C rate also we have discussed. It's a measure of the rate at which the battery is discharged relative to its maximum capacity. So 1 C rate means that the discharge current will discharge the entire battery in 1 hour. And it depends upon battery chemistry and ambient temperature. LTO is the chemistry which in for lithium ion battery which can provide a very high C rate. So these are the two aging phenomena, correct? The next is which of the following is not a firm generation resource? So which one is correct option? Thermal, nuclear, hydro, or solar PV? So what's the correct option? Then not a firm generation resource.
Solar.
Solar, correct. Which of the following can mitigate seasonal imbalance in load and generation? So we are talking about seasonal energy storage here. And for this, we require very high density energy storage devices. Okay. Fast response is provided by high power density devices. High power density energy storages. You are saying B, okay.
Lithium ion.
Lithium ion, relatively, if we see, then lithium ion is in comparison to other three, it's a high power density device, and they are high energy density device. Lithium ion, even if we see right now, commercially they are available for 2 hour, 1 hour, 0.5 also there, maximum up to 4 hour of discharge duration. And since they're trying to have it for 6 hour and 8 hour also, but maximum it will go up to 10 hours. Beyond that, it is not economical. And for compressed energy storage and pumped hydro, they can provide a discharge duration of more than 10 hours and less than 100 hours. For 100 hours, the area requirement will be huge, huge requirement. And hydrogen is one example of seasonal for mitigating seasonal imbalance. What we can say here is lithium ion can provide intraday, can support intraday imbalances. As we have seen in the previous slides also, that it charges by using the excess solar energy and discharges to meet the peak demand, peak evening and morning peaks. So that is mitigating the intraday imbalances. Similarly, pumped hydro and compressed air, they can help us mitigate the interday imbalances. Up to a week, we can say up to a week, 1 week, let's say. I would give an example of this. You can search for it, Snowy 2.0. It is being developed by Australia. Mostly, um, it is still under construction, but very soon it will be operational within maybe 1 or 2 years. And it has an install capacity of 350 gigawatt hours. Very huge capacity. It will be able to discharge for many days, but up to 1 week, maximum up to 1 week. These two energy storage technologies can help us mitigate interday imbalances. But if we want to cater to seasonal imbalances, then we need to. Then hydrogen is one potential candidate. Yes. Any questions? This same thing I have shown here.
You meant to say
Yes.
hydrogen in gas turbines or
No,
fuel
hydrogen
cell or how?
energy storage. No, hydrogen as a gas turbine by using gas turbines for hydrogen, not fuel cell. Fuel cell is a high power density device. It is not.
See, conventional. Now, whatever we are talking about is for the sustainable energy, I mean green
Yes.
energy.
Yes.
These
Yes.
are all that perspectives. So,
Yes.
how do you envisage hydrogen to be stored for so many days altogether when hydrogen storage itself is a very big issue?
Yeah, that is the main challenge. That's why it's a futuristic technology, and they are working. Research is going on to make it a seasonal energy storage. It is still a potential candidate. It's not yet commercially available as a seasonal energy storage. First of all, as you have rightly said, storage is a problem, transportation is a problem, then cost is also a problem. And that's
Hydrogen
why,
itself being very, very dangerous,
yes, it's
and
very
and
volatile.
and it has issues of hydrogen embrittlement. Whenever you use a metal, it
Mm-hmm.
can perforate through the metal and make it very brittle. Is another issue, and if you compress it, then these issues are bigger. And so storage of that much amount of hydrogen for to suffice for seasonal support is, I mean, not practical.
Yeah, that's why it is still a potential candidate. In one way, one method, one substitute of this, they have come up with ammonia for transportation. They will store it in the form of ammonia and use it, then extract hydrogen from ammonia using the well-known Haber's process. But I don't know how means how viable or
The
feasible
the
will it be for
hmm,
a seasonal energy storage. That
the
is, I
amount
don't
of
know.
energy, I mean, you will harness solar energy and then convert it to hydrogen, then convert to ammonia, and
Yes, yeah,
reconvert it back.
efficiency is
So
less.
overall efficiency is
Yes,
extremely poor.
it is. It's very efficiency is very less. But if we want to, if the system requirement is such that when we are focusing on reliability, when our aim is to have a reliable power and we are ready to pay any cost for that, then we have to take resort to any alternative for that. But right now, efficiency is less. Even solar, when we started with solar PV, efficiency was less. Now we are talking about 25% efficiency with perovskite solar cells. So with the research thing, maybe the efficiency will also improve. So that's why it's still a potential candidate. And right now we are not even facing those seasonal challenges because renewable penetration is not that much right now. And those countries which have the high renewable penetration, they already have hydro resources. They have good amount of hydro resources or they rely on gas. They have good amount of gas resources. You can see in European countries, gas resources are quite. They use good amount of gas turbines, gas plants, and instead of coal, they have gas. Major, they have in UK, all the coal plants have been retired, and they have renewables and gas. So yes, it's still a very futuristic technology, hydrogen. How viable it will be, that we don't know right now. We cannot say. But yes, so theoretically, it's one technology for seasonal energy storage right now. And when it matures, we will see whether it rectifies or not. Okay. So
Okay.
these are the three different categories: short, long, and seasonal energy storage. Recently, there is one long duration energy council, long duration energy storage council. You can find its report. And so according to them, the it has members from technological institutions as well as from industries. Several all the industries who are in developing different energy storage, especially long duration energy storage, they are part of this consortium. And they, as per their definition, the discharge duration more than 8 hours is a it falls under this category of long discharge duration energy storage. So this will become 10 hours and this will 8 hours. This will be 8 hours. And right now, no one is into this category because right now it's not even a problem. Okay, then hydrogen storage, production of hydrogen using electrolysis, storage, and then generation using fuel cell or using turbines. Both options are there. Then strategic, yeah, this is you. I think most of you would be knowing National Green Hydrogen Mission. For supporting this, government has started this mission to encourage R&D in this sector. Okay, this is another example of hydrogen. India is also planning to have one hydrogen train. I think where, next year or so. So this is UK's first electric truck, 500 kilometers, lithium ion and hydrogen. It's a hybrid. So hydrogen is used for range extension and it keeps the battery. Airbus is also planning to bring hydrogen powered aircraft. This is done. So next question is, What does the capability curve of energy storage describes? Any idea? We didn't discuss this.
Sir, are you sharing the screen?
Is it not visible?
It's not visible for me. What about others?
But please, others, sir, move.
Yeah,
I'm
visible. Yeah,
okay.
now you went back. Now
Yeah.
we went back to the earlier question.
Yeah, it is visible now.
Okay, now, okay, I think there is some lag. Now, right now I'm on this slide. What does the capability curve of energy storage describes? Is it visible?
Yes, yes, visible.
Okay, so any guess? What's the answer?
TSS operating point on the PQ curve.
Yes. All the capability curves we have as PQ curve. In conventional generator curves also you would have seen. Ideally it should be like this. Like, because S square is equals to P square plus Q square. So if this is Q and this is P. But actually it is not that big. There are many limitations. And this lower bound is even less. And this is not even symmetric. It is something like this. So similarly, storage also, we have a capability curve on PQ with respect to how much reactive power and active power it can supply. And it will depend upon its inverter characteristic. And next question is select the correct option representing the one-time constant battery energy storage equivalent circuit. We have already discussed this for a two-time constant circuit. Which one would you choose? So all the four looks similar.
C.
Right? So which one?
C. C.
Yeah, correct. Good. C is correct. So first of all, it's a voltage source, and then two, and we also know it's RC, and two time constant means it is two pairs of RC circuit. Okay. Oh, what did I do? It is showing none of the above. None of the above option is not correct. Answer is C. Right? C is correct. I will change this. C option is correct. Okay, which of the following are not quality of good cell balancer? Not.
D. D.
Uh, we want everything, always we want everything simple. If we want a simple circuit, then how can control be complex? Right? We want everything fast. We want everything to be efficient, and we want it to be simple. And as well as economical, computationally efficient. So which one would you choose now? C, correct. Circuit should be simple, efficient, and equalization should be fast. You want the cell balancing to happen quickly. Reason for cell imbalance we have already seen. The answer is very simple. Option
D.
D. Right? Correct. All of the above. Yeah, this is I think the last slide or One more question is there. Why linearize the power flow equation? This topic came in that optimal sizing and siting of energy storage. Right now, if you have any question in that, you can ask. Because I was planning to take that up in the next week, where we will come up across these optimization problems. There we'll discuss. If you have any doubt in that optimal sizing siting, you can ask. There in distribution system, the power flow equations, even in transmission system, power flow equations are not linear. We have sine and cosine terms, right? And but for transmission system, we have one kind of power flow model, which is DC power flow, where we make certain assumptions and then we finally get a linear equation, linear model. In markets where we want, because solving these nonlinear equations, we don't have a standard solver for those. It depends on highly sensitive to initial conditions also and takes a lot of time. And if you want to take quick decisions, power system being a very big system, large, Indian grid is a very large grid, thousands of generators, thousands of buses, thousands of transmission lines. If you want to model that in its full glory, then it will not even converge. And we want to settle clear market within real-time market, we want to clear within 10 minutes. Then it will be very difficult. That's why we go for DC power flow models. And to make our life simple, we linearize those nonlinear equations. And the original equations are nonlinear as well as non-convex. And then we linearize them and convexify them. So do you know about convex functions? What is convex function?
Sir, it will
No.
not come to conclusion.
Sorry?
The graph will not come to a ending point. It will go away from the quadrant.
Means
It
is
will not
this a
converge. It will not come to a point.
convex function? A line?
No, this is not a convex.
So converge and convex, these two are not related. Maybe we'll discuss it in the next class, but one simple definition is this: if you have a curve, if you have a function, if you between any 2 points you draw a line, and if that line is above that function, then it's convex. Always above. You draw that line between any 2 points. If you take this function, then function value is more than the line. Function is above. It's not convex, it is concave. We'll see it when we will discuss optimization problem. So we want to linearize systems. We avoid these sine cos terms. And now it becomes linear and convex. We will discuss convex in the next class maybe, or when optimization comes up. And for linear systems, we have good solvers available and we can solve them very quickly. That's why we want to simplify the equations. Then last, I think this is the last question. Yeah, direct cause of permanent failure to lithium-ion batteries due to damage to SCI level. So this is one more. Which type of problem is a distribution network planning problem? This also we have not discussed, right? But do you have any idea? See, mixed integer linear planning. Correct. I think this should. There are many questions left. Do you want to continue or want to stop? Only three, I think. Three questions are left. Continue. Okay, only three questions are left. So this is mixed integer, linear program, non-linear programming.
This slides will upload.
Yes, I will upload it right now. Just after the class, I will upload.
Okay, thank you.
Okay, so non-linear because of sine and cosine terms, and then integer because we want to choose. Network planning problem is which line to build, right? If we have number of buses, 4 buses, already let's say there are these 4 lines. Now, because of increase in load, I have planned possible options for expansion are these. Let's say these 3 lines, right? Now, by optimization problem, I want to know which line to, how many lines and which line among these two select. So that it's a integer variable or a binary variable. So I will associate one binary variable with each line, whether to select this line or not. So it becomes a integer or a integer programming problem. That's why it is non-linear because of network and integer because of these selection variables, which will be integer or binary. Similarly, in energy storage, siting problem. Siting problem is a integer problem. Whether I want an energy storage here, 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 or here. On which bus energy storage should be placed in order to reduce losses or maintain voltage within the bounds or to ensure maximum energy arbitrage, depending upon the objective we want to meet. But the selection variables make the problem integer. Then a 12-volt battery with a capacity of 500 ampere hour is at 80% SOC. What is the depth of discharge? It's very easy, right? Correct. It is 1 minus SOC. Depth of discharge is 1 minus state of charge. So 20%. Next is same question, but in a different way. The SOC is 80%. What is the energy stored? How much is the, yes, correct. So it is 80% of 500 ampere hour. So it is 400. Which of these is not a system operation service? This also we have already discussed while discussing the application of energy storage. So which one is not a system operation service? It is A, right? It is a planning problem. Investment is a planning problem. So this also we have discussed. High ramping requirement and excess RE is there. The net load curve shifts down. Now it is even becoming negative for European and US countries. US and European grids. In India, it's still, in certain states, it is negative. Like Karnataka has a very high renewable penetration, and Karnataka is even exporting excess solar during some days of the years. In India, different states are at a different level of RE penetration. So these are the flexible ramping requirements. We want frequent, quick ramp up, ramp down, and duration also determines how much duration is required. Then quick start, frequent cycling. Those plants which can provide such capability, they right now gas plants can do these things. They are used, but storage can provide such services. Yeah, so we're done with today's session, today's questions. Do you have any other doubt? I will stop the recording. No doubt then we will meet next week, Monday, same time.